Now you've got 28 minutes to prove resolution of singularities.
Jesus. Sorry, guys. I just ran back from another meeting. Yeah, so
Yeah.
I'm gonna. So, so you can knock people over now with these new avatars.
Yeah, that's a bug that's been around for a while. I don't know why that is. Did you just knock someone over? They just sort of fall flat on the ground. Yeah, like they won't see that happening, but from your point of view, it looks pretty amusing.
Oh, really? So I'm the only one
Yeah.
who sees this.
Yeah, I
Right.
don't know why that
Interesting.
happens, but yeah.
Okay. So yeah. So I'm gonna let's say some stuff about resolution of singularities. I'm gonna be super informal here. Let me find my pen. Not gonna be too what's the word, pedantic about a lot of things, and interrupt me if you got any questions. Actually, I have a question. Why is it that every time I go into the boards, I default as blue, like the color? Is that because, is that for you guys as well, or just me?
It's set up that way. That was from when the boards were sometimes whiteboards and sometimes blackboards, so neither black nor
Oh,
white was a good default. But we like
makes
so, for example,
sense.
in the other world deprecation, they're kind of whitish boards.
Oh yeah, they're white. Yeah, yeah, yeah.
So,
That's
so
right.
we opted for a default that is never the right one.
Yeah, there's a power of compromise, right? It's
Yeah.
cool. Yeah, so I'm going to talk about resolution of singularities, and this is not going to be super deep. It's going to be, as I said, informal. And so, the setting we're looking at, right, is we're going to be looking at, I guess, real analytic, right, geometry. Now, I know absolutely nothing about real analytic geometry besides what I've learned from you guys. So, this is going to be this is going to be probably some of it might be wrong, right? So you got to tell me if you catch me doing anything that's not quite legit. But I feel like actually, if you're used to analytic geometry and you go into algebraic world, then you're more likely to just be cavalier with things, right? Going back the other way, a lot of things that you you can do a lot more things in the analytic world that you can't do in the algebraic world, right? So I'm going to define a singularity, right, in the most pedestrian way, right? So um, I'm just going to consider, right, I'm going to consider function f, right, in a, right. I'm just going to, these are just analytic functions. And I mean, I might actually want to say, you know, them as being analytic on some domain U, right, where U is some open in RD, right? And so, to a function like this, uh, you can associate a set of zeros, right? So you can also, given f, right, you can define, right, x, which is the set of zeros, right, which is x in, I guess I'll say it's in U, right, and fx equals 0. Now, I'm not going to, talk about more than one function, right? We've kind of talked about this some time ago. I don't know whether it's part of this seminar series or some conversation we had before. It definitely in Watanabe, right? If you have a real analytic set, right, defined by a finite number of analytic functions, you can just combine them by just adding the square sum, right? And then that will define the same analytic set, right, as a set of functions. So if even if we're interested in zero sets, right, we can still think of, we can still study functions and try and resolve their singularities. And so that's kind of the context which I'll present some of these results. So there's a question maybe I didn't know, I couldn't find the answer to. Maybe Dan, you know this, right? Like, so if you have an infinite number of real analytic functions and you look at the common zero set, can you always reduce this to a finite number and have the same set? Like, does
You're
that work
asking
in
if
the real?
you're asking if the ring of analytic functions is Noetherian, and the answer is no.
Okay, yeah. So that's it, right? So I was trying to say, is that true? I couldn't find a proof. So I'm like, it's probably not. So okay, so we're starting off with finite numbers, right, of defining functions, right? We're going to cut this back down to one. Like this x, right? So we say that x in x is singular. I'm gonna just have a very simple definition. If x is not a manifold at x. Now, I'm not super happy with saying it like this actually, because when we actually go about resolving singularities using Hironaka, uh, at least in the theorem as presented in Watanabe, we're not really doing this, right? We're actually resolving to simple normal crossing, and that's a slightly more involved definition. And I guess I'll just wrap that into the statement of the theorem. But in any case, I feel like I should say what is a singularity and what is not, right? So basically, it doesn't look like a manifold locally. We say singular. You can state this in terms of the tangent space, Jacobian criteria, and whatnot. But essentially, that's what it is. So, what is a resolution of singularities, right? So the resolution of singularities, right? So what we're trying to do is we're trying to make f nicer. So we're going to make f nicer, and that's like making x nicer, right? Because f defines x. Uh, Nicer, I'll define it at x, right? And make, what does make mean? So this is really like you want to pull back, and nicer means normal crossing, or in the language of kind of Watanabe's presentation of Hironaka's results, monomial. You can always express it as a monomial in some local coordinates, which is just like u1 to some power, u2 to some power, the ud to some power, and ooh, what happened there? Yeah, this is because I blame Apple for this. Sorry about that. I was trying to scroll your board, which you can't. What did I
I
write
just
here?
I just I just introduced a palm rejection thing, and you managed to hit the exact limitation of that little piece of code with that little maneuver. So well done.
A palm, like, so you mean if I would just put my hand down, it won't, make it all messed up. But I use two fingers too close together, and that's
That's
normal,
that's
right?
exactly
Right.
what I did to test the limit of it, and you managed to do it without it.
Oh, you got a bigger hand than me. Uh, Singular x if, wait, what did I write there? If we say that x is singular of is a singularity of x if x is not, right, it's not a manifold. All right, thanks. Okay, so all right, super vague what I've written, but I'll state Hironaka's theorem, and then I'll do some examples where we actually, use the main tool in all of this is blowing up. Um, and I think in the statement of Hironaka's theorem in Watanabe's book, he doesn't talk about blowing up in the statement of the theorem. But when you go through the examples, that's what you always do. And in fact, the I don't actually know the full proof of Hironaka's result, but I think you're able to construct these resolutions of singularities by just blowing up smooth centers. Of course, which smooth center would you blow up is really the heart of the algorithm. To say that is kind of a trite way of saying the theorem, right? But it's actually quite difficult to select where you blow up. So the statement of the theorem looks like this. So this is a theorem, Hironaka, right? So we let f be analytic, right? Then there is a neighborhood of 0. So I guess neglected to say that f is 0 at 0. Uh, yeah, maybe I'll say that. And assume f of 0 is 0. F is not constant, right? So it's not the 0 function. Otherwise, that wouldn't work, right? Then there is a neighborhood w of 0, a birational. So I'm gonna use the word birational because I think it makes the statement a little bit simpler. And birational is not super crazy. Essentially, it's just a map which is defined. I guess this map will be defined everywhere on the source, and it'll be almost everywhere an isomorphism, or almost everywhere a real analytic isomorphism actually. So that's what you can think about. And in fact, once we do the examples with blowing up, right, all of the maps that we construct using the blow up will be birational by construction, right? So I'm gonna just pack some of the technicalities in this word birational, right? But it's real analytic morphism. And I'm going to draw it here, so call it sigma. My notation is slightly different from Watanabe's, just because I guess this is how I learned it. So it was hard to follow his notation. I got confused. Right, let's walk over to the next board and finish the statement. Okay. Okay, so you have this sigma, right? Right. We haven't said anything about how to construct this. All we know that it's birational, such that so such that right. What we said earlier about making f nice, we're going to pull back f
Sorry, Kenneth.
along this
You're
map.
a bit
Yeah.
closer to the third board, so the orb is looking over there at the moment. If you could just
Oh,
walk
sorry.
back
Right.
this way a bit. Yeah, yeah, no problem.
Cool. Thanks. Let me just do that again. Right. So what are we doing? Right. We're going to pull back this function right along sigma, such that sigma star f and the determinant of sigma, so that both are both locally expressible.
Where sigma star f is the fancy pants way of saying f composed with sigma.
Sorry, I'm trying not to. I'm trying to have a name for the function without the variable, right? So yeah, yes. Or I could have written it like this, right? Yeah. Okay. Both locally expressible. What did I say? Um, expressible. Man, my notes are terrible. All right, log as fh. Well, I guess I'm gonna be slightly imprecise. I'll write down what I mean here. As monomials in the same local coordinate system. So basically, more precisely, ooh, this is a terrible way to write precisely, and that was a little bit too. More precisely, right? We can write sigma star f as well. Now I'm gonna have a u, which is a local coordinate system, right? U equals, I'll write that in, sigma u is equal to plus or minus u1 k1 u d k d. And the determinant, right? This is going to be some function h u and u1, what is it, j1 u d j d, right? So the same coordinate system, and the kind of assumptions on these K's and J's is that they're all non-negative. So K1, KD, J1, JD, right? They're all non-negative, right? And the H is not zero, right? I guess H is not zero on yeah, some neighborhood, right? Of well, not well, no, sorry, non-zero at U, right? At that point where you've chosen local coordinates U1 to UD. So
I'm a bit confused about the
so
relationship between U, W, W tilde, and RD. Is your RD actually your W or what?
what's RD? We'll
Well,
go
looking
back.
back on the first board, you had sigma from W tilde to W, but what's W?
Oh, all right. So W is the neighborhood of zero. I guess I could have just said that was U, right? But yeah. So I guess W is an open subset of U, right?
Yep.
So
Okay. Mhm.
yeah,
Also,
yeah. Let's do it.
I'm guessing determinant of sigma means the Jacobian.
Yeah, 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 yeah.
Okay.
That's right. Cool. Any other questions? Cool. So we're gonna say these are normal crossing. Right? That's how we're going to define normal crossing. And so yeah, so basically the theorem says that you got this function f, right? It could be a mass at a certain point, right? You can, but there exists this birational map, right, that you can construct using some complicated algorithm that when you pull back f, right, it has this very nice form, right? Locally, it's just a monomial, and and so the geometric way of kind of looking at this, right, is that so what is this saying, right? So the second statement here, the Jacobian determinant of this map, maybe I should have said sigma. This is not quite what I want to write. It's that sigma, right? Yeah, Mr. Sigma. Yeah, so that's basically saying that the so I didn't define this earlier, but when you have this map from W tilde to W, right? It's an isomorphism almost everywhere, but there's gonna be a locus where it's not an isomorphism, and we call it the exceptional locus. Let me maybe I'll just write this in words so we can kind of refer to it. So the map sigma is almost everywhere and analytic isom, right? So there's going to be a locus where it's not, right? So I don't know if this is the best way to define this. So maybe we'll do it like this, right? Um, so there's uh, there's going to be like some. I'm just trying to see whether I can just say this right. Yeah, I think I can, right? Basically, I can define it on the source and say that's where the determinant vanishes, right? So yeah, so the exceptional locus, right? I guess it's the vanishing locus of right. Right, so that's where it's not an isomorphism, and so what this is saying is that this exceptional locus where the map sigma is not an isomorphism also has a really nice form. It's just normal crossing devices. If you look at kind of the local structure of the zero set of such a function, it's just in the section of coordinate planes, right? You're just looking at u equals 0, u1 equals 0, or u2 equals 0, or u3 equals 0, right? Not counting multiplicities. I mean, it may not include all of the coordinate planes because some of these exponents can be 0, but that's kind of what it's saying, right? Like at any point, right, the local structure of this exceptional locus is just intersection of some of the coordinate planes. And moreover, if you look at the function f, when you pull it back, the zero locus also has this nice structure where it's just the intersection of some coordinate planes. It could be just one, right? It could just be one, just like a hypersurface or the hyperplane, right? Or in more complicated situations, you could have like hyperplanes intersecting at a point, but only well, maybe not at one point, but like intersecting, somewhere, right? Okay, so that's all I want to say about resolutions and the theorem. What I'll do in the last few minutes is to compute some examples. And I think I talked for too long. It's already 8 minutes to the end. So let me just do this quickly. These are all from Watanabe's book, by the way. So we can, I'm going to put the numbers there. So let f x y be, this is the most basic example you can take, right? So over the real numbers, you have to, you can resolve this. Over the complex numbers, you don't. This is already normal crossing, right? Because you can factorize this over the complexes. You can't do this over the real, so you have to do some blowings up, or single blow up, I guess, to get a nice form for this guy. So what we're going to do is, there's this point where f is 0, right? It's just 0. And then, we have this map, right? This 0 blows up to be this E, which is copy the projective line. And so how do we do this? So typically what we do is we just blow up, right? And what does this mean? I'll show you how this goes algebraically, right? And basically you have you replace the coordinates x, y with x and y on x on one patch, and then you do the other thing on the other patch, right? X on y, y, right? And so then you pull the function back, right? So these are coordinate patches for the thing on top, right? So this is sigma, right? And so sigma star f, right, what is this on this patch? You just substitute in these new variables and then you factorize it out and then you do stuff, right? So here y becomes y on x over y on x times x, so you can pull out the x squared, right? 1 plus y on x all squared, right? And over here you do the analogous thing where you just take out the y instead of the x, and then you have x on the
Ken,
y.
I think the orb might be looking at the wrong board at the moment.
Oh, did I move? Sorry. Maybe I'll walk back. Is it fine now?
I think
Ye-
so. On my
you're
screen,
right.
you're
What?
standing next to the
Oh,
previous
sorry. I
board.
went to the third. I went to the third board without going. Sorry, guys. Where's Dan telling me off? Let me see.
Sorry, I had to go
Yeah,
and set
sorry. I
up
moved
something.
to.
No problem.
I was doing much better when I was by myself doing the Euclid when you weren't here. Now I'm messing it up. Okay, so coming back to this, right? So I guess I drew all of these. Basically, right, blowing up this very simple function. We're just going to do this algebraic trick. I'm going to just do this algebraically. You replace x, y with x and y on x. On the other patch, y, x on y, y. And then you just substitute in the new variables and this is what you get. And now you can see that the the functions, right, look almost right. They're almost normal crossing. You've got this really kind of strange term here that we can get rid of in the analytic category. But let me just write down, right, the determinant of sigma. I guess here that's x squared, right, and the determinant of sigma, right, that's y squared. So what this is telling us is that the x on this patch on the left, right, the equation defining E is x equals 0. On the other patch, the equation defining E is y equals 0, and and the function just becomes some numbers of copies of E and some other stuff that doesn't touch E. And so there we go. Now, this is still not quite what Hironaka's theorem, as quoted in Watanabe, says, because you have this, he had plus or minus multiplied by a monomial. Here we have a monomial multiplied by some positive function, but positive analytic functions, you can always just wrap this up, square root it, whatever, invert it, and wrap it into local coordinates, so you're okay. So the only thing we're going to be changing here is, I'm not going to do it, I'm just going to say it, is that we can change coordinates and wrap this term up into, I guess, x, and then what this will do is change the defining equation. Well, it doesn't change the defining equation for E, but it changes det sigma in these coordinates, right? So, so that's kind of just a little bit of detail there that you might need if you were to do this and follow and get exactly the result as quoted in Watanabe. So the only probably one more example that I'll write down if I have time is to do this one more time with a different function, and you see it's really the same procedure, right? And the function, I had this, I'm unable to see my notes properly. Somehow I can't zoom in or zoom out. But the function is, so this is example 3.14, right? So the function here is, wow, my phone's really locked up. I cannot, sorry. All right, got it. So function is, so if I don't finish this, you can try this out. Like literally, it's just the same kind of procedure. You replace the coordinates with the ones that I've written before, right? You change x, x to x and y to y on x, and then you factorize, and you do the same thing on the other patch, and you see what happens to these functions on both, to the pullback of f on both of these patches, and then there you go, right? So I'll just do this quickly, right? I'm going to factorize the x out. This becomes x squared minus, this is again, x squared is gone, and it's going to be y on x, I guess, times x. And then plus y cubed is going to be y on x cubed. I guess there's an x. So really, I could have pulled out an extra x, right? X cubed, x minus y on x plus y on x cubed, right? So this is already normal crossing, right? You can verify this. I guess this is on one of the patches, I call it U, B. On the other one, you take out the y, right? You take out y, and I think you can take out y cubed here. So you can take out y cubed, and you get x on y 4, I guess, with a y minus x on y squared. And then you get a 1 here, which means this is not going to touch the exceptional, so you're good. So I guess I'll leave this. I check these both normal crossing. Okay, so I think I'll end it there. There are, of course, like much more complicated schemes of blowing up. You may have to do this multiple times, but essentially, once you've got these new patches, right, you just examine them, and you can choose some blow up to try to simplify this. It's not always going to be blowing up at a point, but for the most part, all the examples I've done have been blowing up at a hyperplane, right? And so that just means that instead of replacing y with y on x, right, you just replace some subset of the coordinates with whatever subset you choose over x, right, over one choice of one of them. And you can do this multiple times and see if at the end you get something that is normal crossing. And the iterations of these procedures for simple examples are usually not super hard, and of course doing this in general is really much more difficult. But in a lot of the examples that you see in Watanabe, or you see in any of the places you find online, right, that's really all you have to do. Yeah, so I think I'll end it there. Maybe you guys can fire off some questions at me that I can't answer.
Okay, let's do it. Thanks, Kenneth. That was good. Yeah, are there any questions? Feel free to ask broader questions. Those will be especially entertaining to watch Kenneth answer. But Technical questions are also welcome. I guess it seems like a fairly technical procedure, but resolution of singularities is extremely famous in algebraic geometry and plays a very important role in many areas outside of algebraic geometry, right? Statistical learning theory is just one, but it's also, has a role in physics and all sorts of other places.
Yeah, but I think some of the more famous examples of resolutions of singularities is not constructed by iterative blowups, right? Like, despite what I said, that's all you have to
Right.
do, is really not. Yeah, like, these G Hilbert schemes is probably the most famous example that I know of. That's the coolest example I know of, where you just do this, G Hilbert scheme, and there you go, it resolves this quotient singularity, and it's like magic, right? But there's no, like, they
Yeah.
don't do this iterative blow-up procedure like I do. This is just for learning and for baby examples.
Yeah, that's right. I guess that's true, that like many things in mathematics, there's kind of existence statements, and then there's, okay, the thing exists, but what's the right way to think about it? So if maybe there always is a resolution, but there's often a way of constructing it that makes clear that what you've done by resolving is something deeply interesting.
Yeah, and also resolutions aren't unique, right? There are, many paths to finding a resolution, and like trying to understand the relationships between these different resolutions is actually quite an interesting topic in itself. I don't know whether this is true for the real analytic category, but is it true that for surfaces it's unique for analytic surfaces, the resolutions are unique? Do you know, Dan?
I don't know.
Yeah, that I don't. But that's the famous result in algebraic geometry, that for characteristic zero surfaces, I think even P, but don't quote me on that. That resolutions are unique, and like strongly unique in that it always factors through the minimal resolution for surfaces. But here, I don't know what happens in the real category. As I said, I know nothing about real geometry.
Are there any other questions?
Dan, you mentioned that it comes up in physics. I was just wondering where does resolutions come up in physics?
For reasons that aren't too different in the final analysis from how they come up in statistical learning theory, I guess. So there are many physical processes that are controlled by potentials or Hamiltonians that are polynomials or can be related to polynomials. And if you think about a vector field, right? So you could easily imagine a particle that's evolving in time according to a field of force given by a vector field. Generically, if you just pick an open subset of whatever space that vector field lives in, you can write your vector field as the gradient of some smooth function. And then, where the vector field is zero tells you where the things will flow from or flow to, right? That's a basic point in analyzing ODEs, for example. Okay, so suddenly you care about functions, smooth functions, and where their gradient is zero. Well, up to shifting by a constant, that's a singularity. And then you can show that the sort of internal structure, so to speak, of that singularity affects the dynamics very strongly. That's a sort of fundamental point of differential topology and singularity theory, which grew out of physics. For example, Arnold is a mathematical physicist and was the first to classify the most elementary kinds of singularities. And then it's just a short step to see that the resolution of the singularity sort of has physical relevance. I don't know a short way of explaining why, but I guess maybe the strongest connection is in modern string theory, where you can make the argument that, if string theory were true, then the fundamental degrees of freedom, which are these strings propagating in space-time, when they encounter a singularity of the potential that lives in their action, they kind of probe the internal structure. That is, the dynamics of the strings can be described by doing some mathematics involving the resolution of singularities. So that's pretty interesting. As far as we know, I don't. Since string theory doesn't maybe appear to be true, I don't know of actually any convincing argument for why resolution of singularities in the Hironaka sense is connected to something very deeply in physics that describes real things. I mean, often the singularities you encounter in the real world are fairly simple ones. For example, the caustics that you see at the bottom of a pool, right, where the light hits the surface, and the surface is uneven, and therefore deforms the light waves. And at the bottom of the pool, when you intersect a surface with those light waves, you get singularities. You can classify what singularities are possible and so on.
Oh, thanks.
Yeah. I'll make a note, Kenneth, that sorry I wasn't around earlier. First of all, maybe it's worth checking just by clicking on the orb cam when you're connected as speaker to check what the orb cam's looking at. Or you can see this black ring around the orb, right? That shows you what the orb's looking at. If you move over here, you'll see that ring adjusts to look. So that's a kind of quick way of checking that it's actually looking at what you think it's looking at.
Yeah, so like in front of each board, there's a fixed location for the orb, right? So if you go over a little bit to the other region, it will just go to the next board. It won't.
Yeah, that's right. I think the sort of misplaced here a bit. It's too easy to get it on the wrong one here. So I wouldn't say this is your fault, but it's natural to kind of stand where you did. But yeah, that's right. The orb will go to the closest.
The boards, right? They kind of if they were all in a line, then you can't. But if they're like this. Where else? You have to draw the line somewhere, right?
That's right. Yeah.
Cool. Thanks, Dan.
Yeah, thanks a lot, Kenneth. I guess it's time to start the code session, which will be a Discord stream. So I'll see you all there.
Cheers. Bye-bye.
Yep.
Thank you.